So good morning friends, I'm Neeraj Gupta and we are continuing this series of video lectures on electrical measurement and instrumentation subject. Here we are discussing the continuation of the last topic, that was the analog measurement of electrical quantities. In the previous lecture we recorded about we talked about the basic methods that were employed to measure the analog quantities and discussed about the permanent magnet moving coil instruments, their basic construction and their working. Now, in this lecture, we will be considering about the extension of the range of those PMMC instruments. We will be talking about further construction of moving iron instruments and electrodynamic instruments here. So, as far as contents with the lecture, the PMMC coil instrument range extensions, then moving iron instruments, the construction of attraction type, repulsion type, their torque equation that we will talk about, and the electrodynamic instruments. These are the most important instruments that are used for power measurements. So as far as concerned with the extension of the range of the PMMC instruments, if we want to talk about the voltmeter range extension, then this is the method. Because as we all know that the PMMC instruments are basically used for the direct current measurements or direct DC voltage measurement only, or DC current measurement only. So voltage ranges of DC voltmeters further can be extended by a series resistance which is selected by a switch, single pole double throw. That it could be selected at any one of these resistance which needs to be inserted into the circuit. So this is how we can extend the range of the instruments. So for multi-range voltmeter, we can design it like that. We can have multiple series resistances connected over here, and whatever resistance, as far as concerned with the input voltage that we are going to measure, can be attached in the circuit. And for finding out the formula for this is given by this expression. The series resistance can be calculated as Rs equals to V over Im minus Rm. Here, V is the voltage for which the desired, that is the desired voltage range in which we want to proceed further. So this is how the DC voltmeter range extension for permanent magnet moving coil instruments could be done. Now, if we want to talk about indirect DC voltmeter measurement, so specifically what we are doing over here, we are connecting these series resistances like that in this fashion. So here, if we want to calculate, this output terminal needs to be connected at any one of the input terminal voltages. It could be at V1, it could be at V2, it could be at V3. So if we want to calculate the voltages which needs to be inserted, so for RS1, this will be the value V1 over Im minus Rm. RS2, V2 minus V1 over Im. For RS3, V3 minus V2 over Im. So this is how we can extend the ranges further. So multiple series resistances have been included, and in previous case, those resistances were connected in series or parallel, and whatever resistance was required was inserted into the circuit. But in this case, these three are all in series, but the terminals, those have been procured out of there, have been introduced, or the complete resistance have been introduced, RS1 plus RS2 plus RS3 by this V3. Only RS1 and RS2 are introduced by V2, and only RS1 have been introduced by V1. So this is another way of extending the range of multi-range voltmeter. Now, next, moving towards this moving iron instruments. So in previous case, the PMMC instruments, we talked about that there was a permanent magnet present in the across the coil of a instrument, and that was actually making it work. But in case of a moving iron instruments, the instrument consists of a stationary coil in which the current needs to be measured is passed. there will be a piece of unmagnetized soft iron core, or the shape of that is of oval shape, is mounted rigidly on this spindle. That is fixed on a spindle. As the spindle will move, that particular soft iron part will move. The soft iron piece is free to move about the spindle and along with the spindle as well. Now, how does this work? Whatever current that we need to measure and that is carried by the coil itself, it produces a magnetic field. It is a general consideration that whenever a current is flown in a coil, that is producing a particular magnetic field. That magnetic field, with that, the iron piece gets magnetized, and iron piece is attracted towards that center of magnetic field, and the pointer which is connected through the spindle is deflecting on the scale, which is calibrated. Here, the control torque is provided either by the control springs or by gravity control method, which have been implemented over there. The damping is provided by the air friction damping, and the scale of such type of instruments are non-linear in nature. Mirror is also provided to avoid a parallax error, that is simple same as like that of a permanent magnet moving coil instrument. So this is how it will work. Now, suppose if we wish to find out that what torque is developed in the case of moving iron instruments, the torque equation that needs to be derived for the MI instruments. So for the MI instruments, if we are considering there is a coil which is carrying a current I, the energy stored in the coil will be given by this expression, half Li square. Now, as this current is changing from a fraction, that is, it becomes I plus Di, the deflection in the pointer becomes d theta. There comes a deflection of d theta, which is resulting into the change of the inductance of a coil from L to L plus DL. So now the inductance of the coil has changed from L to L plus DL because of this I plus Di factor. And the deflection of the pointer has taken place due to the torque TD. Because this deflecting torque would have been introduced, that is why the pointer has deflected. Now, if we wish to calculate over here, the mechanical work done will be torque into the angular displacement. So, TD into d theta will be the mechanical work done. Now, what will be the change in the energy stored in the coil? Previously, it was half Li square when I current was flowing. Now, the current has increased by a factor Di. The inductance have been changed by a factor of DL. So, now the energy stored in this scenario will be 1 by 2 times L plus DL and I plus DL square. So, this change from this half Li square to this will be observed. So, change in energy, stored energy of the coil, final stored energy minus initial stored energy. And if we keep on solving this equation, then the expression is obtained as like that: half Li square 2 Li Di L Di square plus DL into I square 2 I DL Di plus DLX multiplied by Di square minus I square L. Now, if we wish to consider this LDI square, that is nominal change in the current, 2 IDL into DL, these factors to be very nominal, and DL into DI square, we neglect those terms, the expression remains as like that: half 2Li Di DL into I square. From here, the expression comes to be as equation 2, Li Di 1 by 2 DL into I square. Now, further, just think that the change of current from I to I plus DL, the change of current must be accompanied by a change in EMF of the coil. So here, the equation for that could be written as E equals to dLi over dt. So if we partially differentiate this equation, then it will be I dl by dt plus L di by dt. But the change in electrical energy supplied by the source will be voltage into current into time. That is V I T over a period of time. This is your power. Over a span of time T becomes the supplied electrical energy. So it becomes EI dt. So for here, IDL plus LDI multiplied by I. So I square DL plus LI DI will be the supplied electrical energy. Now, according to the law of conservation of energy, the electrical energy supplied by the source is converted into the energy in the coil and the mechanical work done for the deflection of the needle of moving iron instruments. Hence, this equation I square DL plus LI DI, this one, should be equals to the change in stored energy plus the work done, because supplied energy should be equal to the whatever change in the system has taken place plus the work done by the system. So these two should be equal. So while equating them, we consider to have this equation TD comes to be as 1 by 2 I square times DL by d theta. So as I also discussed in the construction as well, that the scale is non-linear. The non-linearity comes by the factor that the deflecting torque is proportional to the I square term. Hence, the deflecting torque is 1 by 2 I square L, I square DL by d theta as given for the moving iron instruments. So it is clear that the scale will be non-linear in these regions. So at lower regions, it will be lesser non-linear. At higher regions, it will become more and more non-linear. Now, the conclusion from that I have to given you is the above torque equation says that we are observing that the deflecting torque is dependent upon the rate of change of inductance with the angular position of iron vane and the square of RMS current which is flowing through the coil. So in moving iron instruments, controlling torque is provided by the spring. Controlling torque due to the spring is given as the K theta, same as like that of a permanent magnet moving coil, where K will be a spring constant and theta will be the deflection of the needle. So if we want to have an equilibrium state, that should be the condition. The deflecting torque must be equal to the controlling torque. So for that, if we equate over here, so the deflection comes to be as this one. Theta equals to 1 by 2 I square by K dl by d theta. From the above torque equation, we clearly observe that the angular deflection of the needle of moving iron instrument is square of RMS current flowing through the coil. Therefore, the deflection of the moving iron instrument is independent of the direction of the current, but is non-linear in nature. So this is the conclusion that we derive from this torque equation. Now, next further we talk about the attraction type moving iron instruments. The construction is something like that. In the instrument is consisting of a stationary coil. The coil will be stationary, in which the current is to be measured is passed. There will be a piece of unmagnetized soft iron, which is oval of construction shape, is mounted rigidly on a spindle. That is mounted rigidly on a spindle. The soft iron pieces is free to move about the spindle and along with the spindle as well. It is placed closer to the stationary coil as depicted in this figure as well. So if we talk about the figure, so this is current carrying coil, which is stationary in nature. These are the this is pointer arrangement. This is damping arrangement. These are the springs. These are balance weights, and this oval shape, you can say this is oval shape moving iron vein which is attached over here. So this is attraction type in MI instruments. There will be some repulsion type as well. Why do we call it as attraction type? The reason for that is this moving iron component that we have placed over here is getting attracted towards the magnetic field which have been produced by the coil, current carrying coil, and because of that, whatever the deflection is being produced is being observed at the calibrated scale. So that is why these instruments are called as attraction type moving iron instruments. There is a single moving iron vein is available in these type of instruments. While we will be discussing with this the counterpart of this as repulsion type, there will be two iron veins. The instrument consists of two iron veins. One is attached to a stationary coil and another one is attached to a movable spindle. So one is attached to this. This is your moving iron vein. This one is moving iron vein, and this is the damping vein. This is fixed one. The upper one or the larger one that you are observing over here is a moving iron one. Now both of the iron veins are magnetized by the magnetic field of the coil. Those are magnetized, and the magnetization is being done in a way that, as you can see, this is dot is perpendicular outside of the magnetic field direction is outside, while cross is direction is inside, and this is the spindle position. These are the two iron veins in which the magnetization will be done because of the because of the energization of this coil or the current carrying capacity of this coil. Both of the iron veins will be polarized or magnetized with the same directions. That is, if this is the north, the same will be the north for the second iron vein as well. Now, as we all know that the same poles repels to each other. So this is the how it will look like. So N and N will repel each other, south and south will repel each other, and because of this repulsion there will be a specific force developed, and this force will be responsible for the movement of the spindle or the rotation of the spindle at which the pointer is being connected. This is the spindle and here the pointer is connected, and because of the repulsion forces the pointer will move on a scale. So this is how these are two specific constructions of moving iron instruments. In this case, this is radial vein and here a coaxial vein. Further classification of repulsion type. One is radial vein, another one is coaxial vein. Now working. Now current to be measured is passing through the stationary coil, produces a magnetic field. Both veins get magnetized with the similar polarities. As a result of force of repulsion, the force is set up between the two veins. This force is responsible for producing a deflecting torque on the movable veins and provides a deflection on a scale. And similar to the general MI instrument equations, the deflecting torque is 1 by 2 I squared dl by d theta. So this was the basic details of the moving iron instruments. Next, moving to the electrodynamic instruments, which are the most widely used instruments for measurement of power. These are very important as far as concerned with the examinations also, and as well as the competitions as well. So electrodynamic instruments basically consist of the two coils. One is fixed, another one is moving coil. The stationary part consists of two fixed coils. Fixed coil is split into two parts so that they carry the same currents. The moving system consists of a coil which is mounted on a spindle which is free to rotate in a space between these two fixed coils. So these are the two fixed coils. F fixed coils. This is moving coil mounted on a spindle with these spring controls. With these spring controls, and basically the coil which is carrying the current is made up of a thin copper wire, and there are air core. The gap between these two coils, or two fixed coils, and the moving main is air. The control torque is provided by the two spiral springs. They also act as connecting lead for the moving coils, and there is a mirror which is provided for avoiding the parallax. And in general, if we represent the ED instruments, those could be represented like that because of the mutual inductance which have been produced by from L1 to L2 or L2 to L1, that is M. These instruments are working. So this is how the basic construction looks like for electrodynamic instruments. Now, how do they work? They basically work upon the current to be measured is passed through the two stationary coils which are connected in series, which are forming a particular magnetic field. Current to be measured is also passed through the moving coils via the control springs. Now the current carrying moving coil is placed in a magnetic field. So according to the Fleming's left hand rule, a force is experienced by the coil, and hence the deflection of the pointer takes place. The torque equation, if we talk about, is in general proportional to the two currents which have been given to the two coils. I1 is the current flowing through the fixed coil. I2 is the current flowing through the moving coil. Now, as a working, when the current carrying conductor is placed in a magnetic field, it experiences a mechanical force, and due to this mechanical force, a deflection of the conductor takes place. And this is how generally the representation of electrodynamic instrument is done in this way. This current coil is considered to have lesser number of turns and thin winding, thin gauge of the copper wire, while the pressure coils are generally having no larger number of windings and comparatively larger cross-sectional area of the wiring. And this is how the load is connected. To avoid burning, the resistance is included in series with the pressure coil. Now, moving coils are moves the pointer with the help of a spring control instrument. A very limited amount of current, because of thin gauge of the wire which is being used in moving coil, is passed through them. There very less amount of current is flowing through the moving coils, so to avoid heating. In order to limit the current, we have connected a high value resistor also in series with the moving coil. Moving air is air cored, and is mounted on a pivoted spindle, and which can move freely along with the coil. So dynamometer type is wattmeter. The moving coil works as pressure coil, and moving coil is connected across the voltage, and thus the current flowing through the coil is always proportional to the voltage. While case of a fixed coil is divided into two equal parts connected in series with the load. Therefore, the basically load current, the larger current is passing through these fixed coils. The reason is very obvious. Using the two fixed coil instead of one, so that the dissipation of the current could be considerably exhausted in the environment, and it can carry the considerable amount of electrical current. These type of coils are called as current coils as well. Now, if we talk about the electrodynamometer type wattmeter, these fixed coils were designed earlier to carry the current of around 100 amps. But now, in a modern wattmeter, they are only designed to carry a current of around 20 amperes to save the power. Because if this amount of power is flowing through the coils, then very large heating and the power losses were higher. But in today's scenario, only this much amount of current is limited, so as to avoid the power losses. Now, the control systems are gravity control and spring controls. Only spring controls are implemented in this case because the moving coil is attached or controlled by the spring controls itself. And the damping system is air friction damping is used, as eddy current damping will basically restore the weak operating magnetic field, and thus it may lead to error. The scale of these type of instruments are used in these type of instruments is coil moving over a range of 40 degrees to 50 degrees is linear on both of the sides. Now, if we want to have a torque equation of these instruments, the torque equation basically can be derived similar to that of a MI instrument. So let us assume the current in the fixed coil be I1 and the current in the moving coil be I2. These are I1 and I2. So L1 will be the self-inductance of fixed coil. L2 will be the fixed inductance or self-inductance of the moving coil. And M will be the mutual inductance of both fixed and moving coils. So if we want to have flux linkage with coil Phi1, fixed coil, Phi1 is L1 I1 into M I2. Flux linkage of moving coil Phi2 equals to L2 I2 into M I1. Total electrical energy supplied to the instrument will be E1 I1 dt plus E2 I2 dt. But according to the Faraday's law, E1 equals to d phi1 by dt and E2 equals to d phi2 by dt. Simply differentiating them, to energy input for that I1 d phi1 plus I2 d phi2. So solving on that, the expression comes to be as this one. Because L1 and L2 are not changing currently, therefore variation in DL1, the variation in L1, that is DL1, and DL2, both are 0. So for that, the equation becomes like that. Then some of the above input energy to the electrodynamic instrumental are stored in the form of magnetic energy, and the rest is converted into mechanical output. So input equals to mechanical plus stored, like that of a MI instrument. So mechanical energy, if you want to calculate, electrical minus stored. So simply we have to just observe the change in stored energy that we have to calculate. Here again making DL1 and DL2 as 0. So this will be the third equation. Now mechanical energy will be I1 into I2 into dm from equations 1, 2 and 3. And TD be the deflecting torque and theta be the change in the deflection. So it becomes equals to mechanical work done is TD d theta. So TD d theta equals to I1 I2 dm, and the deflecting torque comes to be as I1 I2 dm by d theta. This will be the deflecting torque for electrodynamometer type instruments. So these are the references for the study. Okay, thank you.